Hi students. So let us uh, do this second experiment of op-amp, that is non-inverting amplifier using op-amp. So this is the circuit diagram. So where we are applying the input to the non-inverting terminal of the op-amp. So we know that the pin numbers are, this is pin number 2, this is pin number 3, this is pin number 7, this is pin number 4, this is pin number 6, and the pin number 1 5 will not be used in this. Of course they are actually for some compensation requirement which is out of scope for this particular experiment, so that's why we're not connecting pin number 1 and 5. Of course, the expression for the output voltage is given by 1 plus Rf by R1 times Vin. So as we know that there is no negative sign in this, so that's why this is called as non-inverting amplifier. Of course, as per this, the expression for the gain is 1 plus Rf by R1. Of course, there is an extreme for this one. So extreme that you can think of is you can take this Rf equal to 0. So then V naught is equal to V in. So we call it as voltage follower. That means output voltage follows the input when you make Rf equal to 0. The simplest possible circuit you can think of in op-amp is, so this is minus plus, you short this and then apply input to the non-inverting term. So you need not have to connect R1 at all. So just make this 0. 0 by anything is 0. So that's why make this open circuit also. Then also the gain is equal to 1. So that's why it is called as voltage follower. This is called as voltage follower. Voltage follower. So that is one extreme. Okay, other than that, okay, as we did in the previous experiment, so this is a circuit diagram for implementing this in analog discovery. We're connecting input through wavegen 1, and since we want to see the input, we are connecting channel 1 of the scope, that is C1 plus, and we are observing the output at pin number 6 by connecting C2 plus, which is the second channel of the scope. And of course we are connecting plus 5 to pin number 7, minus 5 to pin number 4. This is resistor R1, which is 1 kilo ohm, 1 kilo ohm, and RF is made as a variable resistor using DRB, decade resistance box. So as we did in the previous experiment also, first and foremost thing is that we have to find what is the saturation voltages plus Vsat minus Vsat. So let me do make this RF open. When I make this RF open, it will become infinite. Then the gain is infinite, so I'll get the plus Vsat minus Vsat as the amplitude. Okay, I have applied some voltage which is equal to 1 volt as the input, and output you can see it is going to plus Vsat minus Vsat. So let me measure that. It's not peak to peak I should measure. I should measure the Vmax and Vmin of C2. So let me measure that. So define measurement, channel 2, I will be measuring maximum and minimum voltages. That is, this is my, since I'm using the same IC, so it comes out to be same. It is 4.33. It is, okay, let me just write this as plus of 4.33 volt is plus Vsat minus Vsat is minus 2.84, minus 2.84. So next we have to do some calculation in terms of to find out what is the maximum output possible. So it is said to be minus of minimum of this. So I have minimum of 4.33 and magnitude of 2.88, it is 2.84. So which is the minimum? The minimum is this. So minimum is 2.84. So V naught maximum is 2.84 volt. So now what is V in you can think of. So V in max that can be possible applied is V naught max by AV. So let us take different values of RF starting from RF equal to 0. Let me take this as maybe let me use a different color. so that we can able to make this colorful and then try to have different. Okay, this is, let me use this green color. This is first is 0. Let me make it 1 kilo ohm. Let me make it okay 1k. This is 5k. Let me take it as 10 kilo ohm. Let me take it as 22k, and you can take it as 50k. The gain, of course, we are assuming R1 to be 1k. So naturally, using this expression, I can write this AV as 1, and this as 2, and this as 6, this as 11, this as 23, and this as 51. So with this value of, so what is V0 max possible? It is, I want to find this V in max. V in max is nothing but 2.84 by AV. So 2.84 by AV is, for this particular case, it is 2.84 volt you can keep. And how about this? So it is, let me just use my calculator here. So it is 2.84 divided by alpha A. Calculate, A is now 2. So it is, I can apply 1.42 as the maximum input voltage. Calculate for a gain of 6. I can apply 0. I can apply not more than 470 millivolt, and if the gain is 11, I cannot apply anything more than 258 millivolt, and if the gain is 23, I can apply hardly 123 millivolt. If the gain is 51, I can apply hardly 55 millivolt. This is 55 millivolt. That is maximum possible to apply. So let us apply, these are the peak values. So these are the peak values that you can apply. So let us apply 2 volt here. Let us apply 1 volt. Let us apply, of course, any voltage less than this. So let us apply 300 millivolt. Let me apply 200 millivolt. Let me apply 100 millivolt. Let me apply some 40 millivolt. You can apply any voltage. Even you can apply 50 millivolt. You can apply 110. I'm just giving some possibilities. So let us first start with RF equal to 0. So let me connect this RF. I actually opened it. Let me connect it back. Make this RF as 0. So I just made the RF value 0. Let me see what is. Okay. See, this is my how much is for 0. I can apply 2 volt. I can go up to 2 volt here. I have applied. Let me see what is the output now. Okay, let me run this. Can you see now? It's exactly overlapping. I cannot visualize this. Suppose if you want to see that, you can just take out output now. Can you see this is input? So since output is exactly tracing on the input, you cannot differentiate input output. So that's why if you can see the input peak to peak is 4.01, the output peak to peak is also 4.01 or 02. So now I have applied an input voltage. Okay, input peak to peak measured is, so let me just measure that. So C1 peak to peak is 4.01, output peak to peak is also 4.02. The gain is 4.02 by 4.01. It is actually 1.002. This is what is the gain. So let me just show you that. Where is that? See now, this is input peak to peak, output peak to peak. Expected gain is 1. Your practically calculated gain, of course, upon using these measurements. So practical gain is 1.002. So let us not do this for unity gain. So let us, because unity gain it will always at 0 dB. There is no point in going below 0 dB. So now let us have the value of RF of 1K, and the moment when I just go to RF of 1K, see, if I don't adjust my input voltage, now I'm just making RF equal to 1K. Can you see it's already clipped off here? So when RF is equal to 1K, as per this, when RF is 1K, the gain is 2. The gain is actually 2 now. The gain is 2 now, so input has to be 1 volt or should be less than 1.42 volt. I'm just making it 1 volt. So when it is, okay, let me make it 1 volt and try to see what is output. I'll make it equal to 1. So this is 1. I will see this. See, this is. Now let me just stop it and okay, let me just take, okay, let me measure, let me take few screenshots for my non-inverting amplifier also. Okay, let me start from here. So let me do it for the previous one from the beginning, and let me do it. So let me make this 2 volt, and let me go back to this wave gen, and let me make this RF equal to 0. It's overlapping. Let me take a screenshot here. Let me paste it here. So this is the first screenshot for the, what is this? This is a screenshot for input voltage. What is that? Sorry for that. Okay, I'll just keep this. Okay, just a minute. I'll just keep this. So this is my new thing. So this is for a gain of 1. Now let me have a gain of 2 now. For that, let me adjust this RF to 1K, and let me adjust this input amplitude to 1 volt. This is as per our calculation. Let us see what is peak to peak. So my peak to peak is, you can see input peak to peak is 2 volt, output peak to peak is 3.9. So it is now input peak to peak is 2. Let me just say 2.01. Output peak to peak is 3.92. You can find the gain. 3.92 divided by 2.01 is actually 1.95. Is 1.95. Let me do the network also now. If I do the network, what I'll do, I'll go here, and so because now we are expecting a gain of 20 log of 2. So 20 log of 2 is actually 20 log of 2 is 6 dBs. So even if it is hardly 10 dB, you can able to comfortably see it. Let me make this maybe 20 dB, and then now let me run this. So let the amplitude be, even if it is 1 volt, no problem. Let me apply 1 volt and then run, because this already there at 50 hertz and then 500 kilohertz. Let me run this. You can see I'm getting a gain of 5.8 dB. We are expecting 6 dB. 5.8 is not bad. So now let me stop this and then take one 3 dB bandwidth. So this is my 3 dB bandwidth. So I'll keep this so that I can find the bandwidth, minus 3 dB. So I'm there somewhere here. Okay, this is, see now the bandwidth is 58. So gain in dB is 5.82, 5.82, 806 or 80, and the bandwidth is 58.26. It is 58.26 kilohertz. This is kilohertz, and 5.8 dB is actually 10 to the power of 5.8 divided by 20. It is now 1.94. So this is my gain. This is 1.94 gain that is measured from the dBs. So this is my gain, and this is the bandwidth, 58.26 kilohertz is the bandwidth. So it is 1.94 into 58.26. So gain bandwidth product is 113 kilohertz. So this is again in kilohertz. This is kilohertz. Okay, Leon, let me make the RF as 5K. This is now 1 is there, 2, 3, 4, 5. The moment when I make it 5, I have to adjust my input voltage to 300 millivolt. Let me adjust that. Okay, let me go back to this wave gen. Let me make it 300 millivolt now. Let me run this. I have applied 300 millivolt, and what I'll do, let me run this. Let me also see my network. Let me run this. Now if you can see the peak to peak of input and output, you can stop it here, take a print screen, and then put it over here. Oh, I missed out for 2. Let me just, this is for a gain of 5. Let me do it for a gain of 2. So what I'll do is I'll just immediately change this to 1, 2. I just make this okay. Even with this lesser amplitude it is fine. So, or if you want to make the amplitude as 1 volt, you can still do it. Let me make this 1, go back to this, and then take a print screen of this. So this is just for the purpose of the record. I'm just placing this. This is for a gain of 1, gain of 2, and then we also did it for gain of 5. Let us take the readings and enter it here. So I'll make this 5 now. 2, 3, 4, 5. I have to reduce my input amplitude to 300 millivolt, which is not here. Let me edit this to 300 and there. Okay, let me just measure now. So what is input peak to peak? Input peak to peak is 613 millivolt. Output peak to peak is 3.45 volt. So it is 3.45 volt divided by 0.613. So gain happens to be 5.62. Now this is for a gain of 6. This is for a gain of 6. So this is what I'm having. Just have a look at. So this is the input peak to peak. Input peak to peak should be okay, 300. 300 into 2, that is 600 millivolt. I'm getting it as 613 millivolt. So this is input peak to peak measured. This is the output peak to peak measured. The ratio of this by this is 5.62. I was supposed to get 6. I'm getting 5.62. That is fine. So let us do the network now. When I do the network, please ensure that the amplitude is properly adjusted to 300 millivolt. It should be 300 millivolt. Now run. What is the expected gain? It is 20 log of 6. 20 log of 6, which is 15.56. Let me run this now. Can you see now it is almost there, 15.17. Let me see the bandwidth. Okay, now let me stop it here. Let me adjust this to, okay, now this is fine. This is at minus 3 dB. So let me find out what is the gain, bandwidth, all those stuff. Okay, what has happened? Why this bandwidth has increased? Oh, this is something. Okay, this is 300. Okay, let us now how much I have. So this is for I have a gain of 15.17 dB, and bandwidth would have actually reduced. I'm having it, of course, an increased bandwidth, which is an unusual thing. Okay, let us take whatever we have. So can I just redo it for just for curiosity? Let me just make it 2 and then again run. So I'm just intentionally checking it. So the previous one. So gain happens to be, this is fine. Let me see the bandwidth now. So let me stop this, then let me find the bandwidth. So this should be 3 dB down. Okay, I'm coming down to 3 dB. Where is it? I think there was earlier, there is a mistake. Let me just refind. So this is minus 3 dB, I'm going to minus 3 dB. Okay, this is fine. So this is 174. So previously actually wrote it differently. This is now 174. So this is the previous reading. So let me show you that. This is 174. This is not this. This is actually 174 kilohertz. That's what is there here. See here. This is 174. I think actually I wrote this one now. Okay. Now anyhow, this is the 174 kilohertz is the actual bandwidth for a gain of 2, which is 5.7. Okay, this gain is fine. So gain measurement is fine here. You can see this is gain and this is the bandwidth. Now naturally then this is fine. So you can see from 174 it has reduced to 60 point something. So now let me go to, this is now 2, 3, 4, 5. Let me redo it. Now this is for a gain of 6. For a gain of 6, the gain is 15.17 dB. That is perfect. The bandwidth happens to be, the previous reading it was 60 kilohertz. Let me know. Okay, let us make this equal to minus 3 dB. This is now somewhere here, minus 3. Okay, I'm there at almost close to minus 3. So this is, sorry. So fine. So it is 60 point. So whatever reading that we have taken now for this is fine. You can see it is 15.17 dB, and this is my bandwidth. So let me find what is the gain bandwidth product here. So what is the gain bandwidth product for this? It is 5.8 multiplied by 174, which was 1009 kilohertz. So here what is 15, get 10 to the power of 15 point, 10 to the power of 15.17 divided by 20 is actually 5.73. This is 5.73 multiplied by 60.7 is actually, oh wait just a minute, let me first, maybe I made a mistake here. This is 348. This is not, this is actually 1.94 multiplied by 174. It's actually 337. See, whenever I'm doing this gain bandwidth product, I have to multiply the gain in volt per volt to the bandwidth. So which is 1.94 multiplied by 174, which is 337 kilohertz. And in the next case, it is 5.73 multiplied by 60.72, which is 347. So these two are pretty close. So this is as per our expectation. Let us go to a gain of 11. So I'll make 10K one. I'll make others as 0. I have to apply 200 millivolt. So let me apply hardly 200 millivolt in my wavegen. Where is my wavegen? This is my wavegen. Let me apply hardly 200 millivolt. Let me run this. Let me go to this and then run this. Okay, let me stop now. Take this. Okay, this is input peak to peak is, of course, this maximum is not required. Let it be there. So C1 peak to peak is 411. This is 411 millivolt, and output peak to peak is 4.28 millivolt. So now it is, of course, ensure that the outputs are not clipping anywhere. They should not clip and they should also not clip. So it is now 4.28 divided by 411 exponential minus 3. So you have a gain of 10.41. So this is the reading what I have now. This is the input peak to peak, output peak to peak. This by this is 10.41. Okay, of course I missed out some screenshots. Maybe you can just manage while doing it. So this is, okay, let me take the screenshot of this, then put it over here, which is we have restored the frequency response of, this is the frequency response for maybe one of them we missed out. So what is that we had was, we had the frequency response of because we didn't take the frequency response of any of them. Okay, you have to take the frequency response. Okay, now this is for a gain of 11. What I'll do, I'll go back to my network and reduce the amplitude to as per our requirement. It should be how much? I have to have a gain of, this is for okay, let me make the amplitude as 100 millivolt and let me run now. Okay, since the gain is beyond 20 dB, you can see this dotted line. So this is an indication that I have to change my scale. Let me make it 50 dB because expected gain is 20 log of 10.41 or 20 log of 11 is the expected gain, which is 20.82. You can see 20.8. So let me stop now and measure the 3 dB bandwidth. So this is my 3 dB bandwidth. Can you see now this is almost minus 3 dB, and let us find what is the bandwidth and all those stuff. So now the gain is 20.5 dB. The bandwidth is 52.36. So the gain in dB should be converted to volt per volt, which is 10 to the power of 20.8 divided by 20, which is 10.96. It is 10.96. So now it is now 10.96 multiplied by, so it is, this is now into 52, which happens to be 569 kilohertz. There's a slight variation from the expected value. The gain bandwidth product has actually increased, but certainly you can see as the gain increased from 5.73 to 10.96, the bandwidth has actually reduced. So of course the bandwidth would have reduced more. So there is some issue with this one. So we'll just note, okay, we can't do anything much with this one because this is how is our response coming. So let us measure what is that we are getting, but make sure that we are applying proper input voltage and we are doing that. Let me run it again and try to see what is. It has now reduced. Just a minute. Okay, let me just go back to mine. This is now gain of this is gain of 11. This is, I just made this equal to 11. So for a gain of 11 I have 20.44, which is my previous reading, but it was 20.5. the bandwidth is almost there, you're almost there. Okay, that's fine. So whatever readings we obtained for a gain of 10k, for a resistor of 10k is fine with this. So let us do it for 22k. So I'll make this 22, and my input has to be 100 millivolt. So let me reduce the input voltage to, okay, this is my input. Where is my input? Let me reduce my input voltage to 100 millivolt. This is 100 millivolt. Let me run this. Let me see my output. Let me run this. So, and we are looking for a gain of 23. we are looking for a gain of 23. So let me now stop it. So input peak to peak is 209 millivolt. Output peak to peak is 4.38. What is the gain now? It is 4.38 divided by 0.209. So gain happens to be 20.95 for a gain of 23. That's fine. Okay, you have to have some variation. For a gain of 23, I have my input voltage at 209 millivolt peak to peak. The output voltage is 4.38. The ratio of output by input is 20.95. Let us see what is the gain in dBs. So gain in dBs, 20 log of 23 happens to be 27 dBs. So I should get 27 dB. Let my input amplitude be 100 millivolt. Is mean okay, this is fine. So this is at 50. That is fine. I have to get around 27 dBs. You can see you have almost 27 dB now, 26 point something. Let me adjust this to a bandwidth of minus 3 dB down. So let me just put it down here. This is, I'm there at minus, this is minus 3 dB. I'm there. So let me know what are the, so bandwidth gain in dBs is, gain in dBs is 26.8 dB, sorry 78 dB, and then the bandwidth is 27.9 kilohertz, 27.9 kilohertz. So gain in volt per volt is 10 to the power of 26.78 divided by 20, which happens to be 21.82. 21.82 multiplied by 27.1. Yes, it is 593. Okay, this is what the gain bandwidth product I'm getting. See now, this is the latest reading. For a gain of 23, I'm getting a gain of 20.95 in my time response. In my frequency, sorry, in my network frequency response is almost close to 21.82. The bandwidth has reduced to 27 kilohertz. The gain bandwidth product is 583. Okay, let us do the last one. The last one we have to make this as 50k. This is 2, 3, 4, 5. I made it 50k. Let me apply hardly 40 millivolt. Let me do the network first. This is 40 millivolt. How much is 20 log of 51? 20 log of 51. 51 happens to be 34 dB. You can see you almost have 34 dB here. Let me stop this and then make this as 3 dB down. Do you have a 3 dB down? Yes, I'm there almost at 3 dB. See now I have a gain in dBs as 33.74 dBs. The bandwidth is 16 kilohertz. 16 kilohertz. So it is 10 to the power of 33.7 divided by 20 is actually 48 is the gain. 48.4. 48.4 into 16 happens to be 774. Because there is slight inconsistency. This gain bandwidth product is not remaining constant. Okay, this is because of the op-amp quality. We don't have a very great quality op-amp here. So, but I can see we are expecting a gain of 51. We are getting a gain of 48.4. The bandwidth has reduced to 16 kilohertz. So let us do this time response. For time response, let me apply a 10 millivolt signal. Sorry, how much is the amplitude you can think of? I can apply even 40 millivolt. So this is 40 millivolt. What I do, I'll apply 40 millivolt signal. This is, let me make this 40 millivolt. This is 40 millivolt signal is applied. I will run. I will go to the network. Let me run this also. Okay, let me stop this. Let us take this reading. The input is 91.77 millivolt and output voltage is 3.82. Of course, if I take the ratio of this, let me come to this. So what is output? It is 3.82. 3.82 divided by 91.7 exponential minus 3. So you actually have a gain of 41. This is actually a gain of 41 you're getting. But actually this cannot be 91. You are supposed to have 80 millivolt. Suppose if I take 80 millivolts as the amplitude, so if it is 3.82 divided by 80, it is 0.08. So gain is coming out to be 47. So we expected a gain of 51. So this is close to 47, which is not too far away from the expected value. So this is too far away from 51 because there is an error in the measurement of this input amplitude. You can see this input amplitude. Let me just make it something like this. Sorry, here. So let me make this 50 here. So let me again run this. So this is now it is fine. Can you see now it is 83? If I take it 83 now, so if it is 83, so it is 3.82 divided by 0.083, which happens to be 46. So this is 46. Okay, while measuring the amplitude, make sure that you properly see the waveform. So if the scale is too much, you may end up with some error in the readings. If I make it so and so, can you see now you're not properly visible? So when you run this, so this reading will be not a proper one. Can you see this is 91? It is showing so many things. So make sure that you're properly seeing the waveform. Make it something like this. Now it is fine. Or even if you make this maybe something like this, it is much more better. Can you see now it is 83? So this way you can able to comfortably do the things. But one thing is, so here it is not very consistently constant, but this is fine. At least you can see as the gain increases, bandwidth is reducing. So you can see it is going from 1 to 2 to 6, 6 to 11, 11 to 22, and then so on so. But the gain is, sorry, bandwidth is reducing from 174 kilohertz, 60 kilohertz, 52, 27, and 16 kilohertz. So at least that trend is there, but this is not fairly remaining constant. But still, okay, this is how we have to do the experiment of non-inverting amplifier, verifying the gain and the bandwidth of the amplifiers. Thank you.